So, apparently we're live on YouTube now. So, hello everybody. This is a meeting together in EPFL and Waterloo.
I'm not seeing you on YouTube right now, but
It will take some time.
yeah.
Mariana, please silence the mic. Yeah. So, we're here to give a starter presentation about Dotty, the new compiler for Scala, and to answer basic questions how to get the environment set up quickly, and to go into what are the trees and symbols. There will be follow-up talks which will go into other topics, but that's our starting one. So I'm Dmitry. I'm a student of Martin Adersky. I was the first one to join him working on Dotty, and I helped out to develop some parts of the Dotty. So first, to get started with Dotty, you need to clone it from GitHub, obviously. So the link to clone is in the LAMP group, and there is a Dotty repository, and that's the main repository where the upstream Dotty happens. There is also another repository, which if you'll be contributing, you should be aware of, which is the repository where development happens, which is in the organization Dotty staging, and there is a repo Dotty. The intention is that what happens here should be quite clean and is what's shown to the public. It should be quite easy for them to understand what's the main version of Dotty. While here, research happens, bug fixing happens, and a lot of garbage accumulates. Okay. The main repo is used to make pull requests, it's used to open the issues, and it's used to track the state of everything. So in order to get the environment set up, you first need to clone Dotty. You use Git for this. Try to make the text type over there. So you clone the Dotty repo into some folder. And one more thing that you need to set up Dotty correctly is you need to clone the specific library which is supposed to be working with Dotty. At the current moment, this library is maintained in my fork of Scala repo. So you need to clone additionally this repo to a specific folder called Scala. Those repos are quite big, so it normally takes quite some time to clone them, but because I'm in a fast wireless connection, it's really fast. And you want to check out the branch called Dotty library in the Scala version. Okay, now Dotty uses SBT to build. So there is quite a complex build here, which you don't need to know how it works, because it can be easily invoked using SBT itself. So if you start up SBT here, you should be able to get your rolling fast. It will download some dependencies, set up SBT. Normally it takes quite some time to start, so when I do my development, I fire it up once and I don't shut down in weeks. I just keep it open forever. So if your call compiled here, it will compile entirely. So while it is compiling, I'll show you how to set up the IDE. So I'm using IntelliJ for development. It's my IDE of choice. And IntelliJ has recently, a year ago or so, added support for native SBT projects. It means that you can just import the Dotty configuration as is, and it will use the existing SBT setup to figure out how to set up the IDE. So I will show you how to import this new Dotty that we just cloned. So you can either press import or press open. It actually does the very same thing. You just navigate to the folder, where you downloaded it, and you'll see this, you see bluish, Scala-ish thing, which is actually a symbol of SBT. IntelliJ this way shows you that it has discovered an SBT project there. If you open it up, it will be able to import it. So if you want Java 1.8, Dotty doesn't support any version of Java pre 1.8 first. And anything else should be fine with it. So now it's going to ask multiple questions to SBT to figure out how to set up the project, and it will tell you that there are a lot of sub-projects there inside Dotty. Dotty is actually not only a compiler, there's a documentation tool, there is a CI tool, there is standard library which ships with Dotty, there is benchmarking harness, there's a lot of stuff inside there, and in most cases you don't need all of it. So what's going to happen now is IntelliJ is going to show you all of this stuff and ask you what do you actually need out of all of it.
Dimitri?
Yeah?
Do you want to use auto import in the SBT configuration?
So what auto import does is if you were ever to update the SBT configuration, it will re-import it and reset up the entire project. For me, I frequently modify a build file for a reason I'll show you later. So if it was to re-import it after every small modification, it will be very slow for me. I don't have this mark ticked.
Okay.
For somebody else, it may be convenient because if you don't modify it frequently, you just want to get everything done. So there are a lot of projects here, and as I said, in most cases, you don't need all of them. The common setup, which I believe will work for most of you, is just disable everything and enable Dotty. It will tell what are the dependencies of Dotty, and this will be the minimum you want to get working. As you can see, it has only a very small subset of all the stuff available here. It also helps, you can actually import everything, but if you don't have a powerful machine, then it can be quite hard to navigate through it, and it will be lagging a lot. Okay. Yeah, so here it will import it. In the meantime, while it imports it, I'll give you a small hint about how to make it work faster. So in IntelliJ, there is, near the actual executable of IntelliJ, there is a file idea VM option. That's the options that IntelliJ uses to start the actual VM. And there are actually two files here, IDEA and IDEA64 VM options. Those will be defining which platform do you run. By default, it has quite conservative setup. Specifically, it has something like half a gigabyte for entire IDE. The sole index for Dotty is bigger. So if you were to use IntelliJ with Dotty, you want to make these numbers be slightly bigger and instead at least be a gigabyte, maybe several gigabytes. So that's what we did. I've changed these files, so to show you the difference between the two. So as you can see, I bumped up memory quite a bit. I bumped up minimal memory by a factor of almost 10, and the maximum memory by a factor of almost 8, and also reserved code cache. For those who want to trick more, there are nice ways to change how GC works here. Who want more responsible IDE, but that's I leave free to discuss. Okay, so in the meantime, we have Dotty working here. So now we should have all navigations working. So in particular, if we type some name of the class, we'll be able to find it. The entry point to the entire Dotty is the compiler. So because it's a new project, it asks us what Scala library are we actually using. At the current moment, Dotty uses Scala 2.11.5 for internal reasons to actually reuse some of the infrastructure of it. It may change in future. When you'll be watching this video in future, please look up the documentation.
And the documentation is on dotty.epfl.ch. If you click on the docs link at the top right.
Yeah. Yes, thank you, Guillaume. Okay, so compiler is an entry point to the compiler. It has the initial phase plan, which will be executed. Dotty, as most compilers, are
is built using several modular things, which are called phases, which transform the compilation units and actually build up the compilation. We'll go in more details what are those in the future talks, or if we'll have time today. But today I want to start with one of the commonly used objects inside Dotty itself, which are trees. Trees are objects which actually represent what user wrote. They represent methods, they represent expressions, they represent classes, and they represent it in the same way how user is more likely to expect it to be. So that's a tree which has some sub-expressions inside them, which can refer to other values, and those trees have some attributes. It should be noted that when I'm saying that it represents a tree as if user written, I'm actually simplifying. Dotty has two types of trees. Dotty has untyped trees, which are in untpd, which stands for untyped. And those trees actually are specifically what user wrote. Those are the trees which are generated by parser. There are some trees which only exist in this way, in the untyped word. For example, while do and do while, and for cycles. Those trees are disregards and simplified in a sense when they are typed. Because of this, most of these trees actually disappear while going through type checking. And after type checking, we instead have the TPD trees. The typed trees not only represent the syntax as what user wrote, they actually represent additionally, well, types which are contained inside them. And the typed trees contain semantic information about what does it actually mean what the user wrote. So now, going back one step, when I'm talking to the trees, it should be noted that most of the Dotty compilation pipeline, similar to the Scala C compilation pipeline, shares the same representation of whatever it's compiling for most of the actual compilation. It's quite uncommon among compilers, and it's frequent that they change representation. They go to something similar to SSA or another way of encoding stuff. In case of Dotty and Scala C, the representation stays the same, and the representation is trees. It should be noted that those trees use several optimizations to become more efficient. In particular, they're immutable, which means that you can reuse the trees as long as you don't change them. It's supposed to help a lot with the memory consumption. Now, let's go quickly around the most common trees that you will ever see. So the easiest tree, I believe, is ident. That's just a reference to already existing definition. Let's say if you refer to a variable, the most likely that you're using an ident refer to it by name, in a sense. Ident is a representative of what we call draft trees. Those are trees which refer to something. There are other ways to refer to something. In particular, you can select a member of already existing thing. So if you were to access a field of a class, when you're accessing this field and you're saying that this field is called foo, so you say a.foo, the a will be an ident, and foo will be a select from this ident. In some cases, when we select a symbol, it's ambiguous which you select. So there are some more specific kinds of selects available here, but we won't go into those details now. Other trees which are commonly used are, and those which have obvious meaning are this and super. So this is a reference to the current class, and super is a reference to a superclass of the current class. The tree which is applied is a method application. So if you were to select, instead of selecting a field, foo, in case foo is a method, after you selected it, you may pass it arguments. So this tree will be represented as a apply of select of ident. So ident A, select foo, apply 1, 2. So the apply node contains the arguments which are being passed, the args, to the invocation. It's important to note that in Scala you can have methods which have multiple argument strings. So after you select the function, like we did before, it may be the case that you may have multiple applications following one another. And then you'll have multiple apply nodes around you. Yeah. Okay, now, assuming we're done with apply nodes, there is type apply. So when we're talking about apply nodes, we're applying a member to a term, in a sense, to a value. We're passing it arguments, which are values. You can also pass a type. So if you had a method foo, which takes an argument t, and the value of this type t, and does something with it, in order to apply this foo, while in Scala you write something like this, after type checking, there is a t here, which is expected to be instantiated. In the example which we're passing, the t is actually instantiated to int. So the corresponding tree here, before passing the value 1, has to pass the type int. So the tree here will look like ident foo, and then type apply. Int, and then apply around those which passes the actual value 1. So on this example, it's quite easy to see why do we call them trees, because all this node actually builds a directed graph. When we call trees, we actually simplify it a bit. We can use structural sharing aside. It can actually be a DAG, directed acyclic graph. Another thing to note on this example that is if you see the foo reference here, though it's a method, the access to it is done through ident. Ident and select in Dotty are quite interchangeable. Whether you can access something. Yeah?
I have a question. So in which cases do you get a DAG? When do you share trees?
So because trees are immutable, for efficiency, you can reuse the same tree in multiple locations, and as long as it's literally the same. To give you an example, there is a single empty tree in entire Dotty, while it's actually put in multiple locations where we say that there are no children inside this tree.
Mm-hmm.
So at least given the example of the empty tree, Dotty has a non-directed cycles, so it's not a tree.
So Andre, a more common example maybe is if you import, so you say import and then qualifier and then maybe dot underscore. Then if you use one of the imported names, it will always convert that into a select node with the import qualifier as the prefix. And that one will not be duplicated. So it will be the same for all the identifiers that you import from that qualifier.
Okay.
There are several other examples, but I think two is enough.
Okay.
Yeah, so that's an illustration of what Martin said. So if you were to import package blah, which has a member bar, this bar, while type checking, will be desugared to a select from blah bar, and this select will be shared between everything which you take from the package blah. This sharing is temporary. While the trees are being transformed by other phases, they can be copied on a copy and write basis. But a lot of this sharing is persisted during the entire compilation pipeline. Okay, now, when we're done with those trees, let's go with the next ones. So the literal is constant. If you have number 1 of number 2, that's literal. New refers to a type which you're constructing, it's actually quite a complex node, which inside itself has a tree, and this tree is assumed to represent a complex type which is being constructed. Now we're going to quite complex nodes, and constructing those nodes can be quite involved. That's one of the main reasons why the TPD and untpd objects exists. They provide a convenient API to construct common classes. So for example, they provide helper methods to call new. So if you want to construct a type TP, you can call this new TP. And it will create the correct tree for you. Okay, now continuing with the trees. Typed. The type tree is used when you have a type description. So let's say you want to have a value 1, but you don't want to know that this is an integer. In Scala, you will write something like this, which means that you're widening the type by hand. That's an example when you have a type tree. Named arguments. You can have methods where some of the arguments are provided default values and or names. So if you have a method foo, which has arguments bar and bool, which are int and int, what you can actually do in Scala is you can give those arguments out of order. By giving their explicit names. Named arg is a tree which will be the tree of passing this argument. It will be in the right location inside type tree, but in the location where the user wrote it in untyped tree. So, important thing to know, inside untyped trees, the arguments inside apply, if user used named arguments, can be in quite an arbitrary order. Inside the type check tree, they will be in correct order, but you'll still be able to see if it was passed using named arguments. Okay, now the next tree, assign. Quite a simple tree. If you have a mutable value and you assign it a new value, this tree will be called assign. This tree assigned will be used here. It's important to note that in case your thing is a field, then when you actually assign the field, you can have quite a complex expression here which says what you're actually assigning to. So in this example, we allocated a class and we assigned the value of the field there. The class is now gone, but the tree is still there. So when you're working with assigned nodes, though they look like they have left-hand side and right-hand side, be aware that the left-hand side doesn't have to be simple. It can be a complex expression which has everything up to while cycles inside it, which is actually the way how you compute what are you assigning to. Okay, now, block. Now we're going to the trees which represent control flow. First one of those is block. So if you have a block where you do some stuff and then you return an expression, that's a block. Block is represented by a series of statements which follow one another, and then the expression which is the actual value returned by a block, which can be seen here, the stats and the expers. So now in a simple tree, if. So if obviously represents an if of type cont, event, else. Where cont, else, event, and else are sub-expressions inside the if. Once again, important thing to know that you shouldn't assume that condition is a simple thing. Condition inside itself can contain class definitions. You can do whatever you want here. You can define a new class D and check UD dot hash code more than 0. Nothing prohibits you from doing anything in set conditions in Scala. So be aware that everything can happen here. Okay, closure. Interesting kind of tree. Let's say you had some list, and you were to map this list. The question is, we know how to represent this. We take list, we apply it to 1, we select map. How do we represent now the argument that we pass to map? That's where the closure comes in. Closure is a tree which more or less defines a lambda. In this lambda, there are some environment things which this closure can capture. So, for example, in whatever we wrote here, if there was a val z here, and this closure was to use x plus z, then in some moment of pipeline, you may know that the closure captures z. At the current moment in Dotty, the only place where you can rely on this is around lambda lift. Before this, you're not guaranteed that the thing is filled. Okay, now math refers to a method which will be silently created to actually define the closure. So let me not to jump between the two. So what's going to actually happen in this example is there will be a method defined here which implements this. Def anon dollar of x equals. That's how it will be actually compiled. And the type int is inferred. So what's happening here is actually it will look like this. And this anon will be the closure tree. And you know that this anon through this math reference. The TPT here tells you what kind of single abstract method type does the thing implement. Before Java 8, the only lambdas which Scala had were Scala functions. After Java 8 and Java introduced lambdas which can be anything from functions up until runnables, any kind of interface which has a single method non-implemented can become a parent for lambda. So closure now tells what kind of type does this lambda actually implement and what kind of empty method does it fill. Okay, now when we're done with lambdas and closures, let's proceed, but it should be noted there are a lot of details hidden around how these closures are compiled. In particular, one thing worth noting is that not all closures, which are closures and anonymous functions for Scala, will become closures and anonymous functions for JVM. We have different agreements about what closures are, and not all of them will be optimized by the VM, but most of them do. Okay, now when we're done with closure, we have pattern matching related trees, match and case def. So if you were to write the code, this entire tree will be represented by a match, where you're matching a literal, and then you have a series of cases. This can be seen inside the tree, which represents the match. So it has a selector, which is what are you matching on, and cases, which indicate what are potential choices where you can go. The cases are always case defs. The cases themselves have multiple fields. The first one is pattern. In the example where I wrote, the pattern here is A, and the pattern here is underscore. The pattern is what particular shape are you looking for, and that's the first way how you filter in pattern match. The guard is an optional tree which is present if the user has written an if. If user didn't write an if, you'll have an empty tree here. And the body actually contains was it to be executed in case you enter the specific alternative. In particular, in this case, the body will be 2, in this case, the body will be 1. It's worth noting that the actual pattern here is taken from a set of trees which are used to represent patterns themselves. Those trees are trees like bind, alternative, unapply. It's very uncommon for people working on compiler to need to work with them. Those trees have a lot of details which are very important but easy to overlook. In most cases, in order to understand what does the tree actually do, you need to analyze the entire pattern. Every tree in isolation doesn't explain what it did. Okay. Now, after we've done with this quick intro to pattern matches, we have returns. So return is a simple tree which says that you're going to finish execution of the method, and the method that you're going to finish execution is listed in the from. If the from doesn't contain a reference to a method and instead contains an empty tree, it means you're finishing the method which is the most enclosing one. In some examples, during transformation of Scala, we can actually have returns which go outside the nearest enclosing method. I'm pretty sure you can't write this in Scala, but during the compilation pipeline, we create those trees. So the expression that you return here is expected to be of the same type as the return type of the method that you're returning from. And the return tree itself, because it doesn't actually have the value, because it doesn't continue execution, it will always have the type which is a bottom type. In case of Scala, that's nothing. Okay, now for the try. Try is a tree which encodes the fact that you're going to perform some computation, which is noted by expression, and when this expression fails by throwing an exception, you're going to see if the exception matches some of the cases. The cases are of the same kind of those which are used inside the match trees, more or less. And you can, in addition, have a finalizer which is being executed independently whether any of the cases actually match the exception or not. Yep. Now, going back to our trees, cyclitteral. In Java and in Scala, you have arguments where you can actually pass multiple values at once. So if we were to define a method which may take arbitrary number of integers, like this one, then what you're going to do here is you're going to pass multiple arguments at once. And you want to be able to know that those arguments actually correspond to the same argument in the definition, not to different ones. So the secliteral will be used in this case. After some moment in the pipeline, you can also see Java secliterals. The difference between the two is the runtime representation and the way how they're erased. Scala secliterals are represented as Scala collections, while Java secliterals are represented as the underlying JVM arrays. Okay, the next trees are inlined. This is a tree which is a result of inlining a call by typer. I won't go in details about what this is, but if you're interested to see what it does, there is a SIP, which is called inline in meta, and it explains what it does and how it works. In short, it's here to implement generic programming and meta programming. Okay, so type tree is a tree which represents a type. It's used when you want to actually represent let's say, the type that you pass to type apply, or the type that you pass as self-type, or any other location that you expect to type. And there are some specific kinds of type trees, like singleton type tree. That's the case where you refer to a value of which there's a single entry. There's only a single runtime value. Ent types are types which are either left or right. So let's say if you want to have either integer or double, that's an both integer and double, because that's an ent type. Then you have an ent type, which means that you're actually looking for an intersection of requirements specified by both types. The best friend of the ent type is an or type, which means that you're looking for something which is either of one type or another. So both int and double will do. Okay. The next type trees are more complex, and I will postpone this discussion up when we discuss the actual types, because they resemble the types in the type system. But to tell you quickly that most of the types which can be represented by the by users, types which can be written by users can be represented by trees, but not all types represented by type system can be written by users. So the types representable by trees, if you were to use those, are slightly incomplete. Okay, now we have the binding, turn dependent, and apply. Those are the trees which are used to define pattern matching. And now we have the actual definitions: valdef, devdef, and typedef. Valdef defines a field or a local variable, which is given a name, which has a specific type, and has the right-hand side. You can see here that there is a lazy tree here, not a normal tree. The lazy trees are specific kind of trees which Dotty can decide to postpone computation of. In particular, if you're reading this tree from outside source, like Tasty, you may not be interested to see the entire valdef. You may be only interested at what's the type of the valdef, what's the signature of the valdef, which is the most common case. And it's not worth reading the tree, the implementation, unless you actually need it. So because of this, we have some points of laziness here, which are lazy trees. Okay, so depending where the valdef is, it will be either a field or a local variable. If valdef is inside the body of a class, it's a field. If it's inside the method or a block, it's a local variable. The easiest way to know whether it is a variable or a field is actually not through tree, but through types and denotations and symbols, but we'll talk about those later. The important point here, which we'll see starting from valdef, and we see it in most trees, that if you're trying to understand what does a tree mean, the best way to do it is to look at its type. The form of a tree doesn't tell much, and the form of a tree in many cases may be ambiguous. Okay, now devdef. Devdef defines a method which is given a specific name, which has some type parameters, type arguments, and it has some value parameters, which may be multiple, and that's why it's a list of lists of valdefs. It has some specific return type, which it returns, and similarly, it has implementation, which we may decide to read later. The last kind of definition which exists in the type tree is a typedef. You're defining a type. This typedef can be either a class or a local type, and it will be represented differently inside the tree itself. So the common case when you think you're defining a type is you're defining the class C, which has fields. Another tree which will be represented by a typedef is if you define type A like this. In order to know from a tree whether that's a class or a type, the way to do it is to look at the right-hand side. For classes, it will be a template. But as I said in the previous example about valdef, this allows you to give information. It allows you to find this information, but that's not the best way to do it. The best way to do it will be to look at the type, whether the type of the thing is a class or whether it's a type. But we'll go to those later. Okay, now we just had a glass over this template, which is a thing which defines what's the body of a class. Template has a constructor, which will be a constructor of the class. So if we were to write the class foo a leads, ls plus 1, the required is 2. So that's actually the constructor of the class. And that's what this dev will be referring to. Up until the middle of the pipeline, you don't have the actual constructor created. For example, the assignment here should become a part of constructor, but it will only become part of it after the face constructors. Before it will be part of the template. One more thing which is part of the template is parents. So if our class foo extends serializable, then you'll see this in your parents. One more thing that you can see is, yes?
So what if there's other code in the class, like other than fields and methods and initializations?
Like this?
Yeah. Yeah. So where does code show up before it's put into the constructor, or does it?
Or
does it go into the constructor right away?
So it will go into constructor after the phase constructors. Before this, it will be in the actual body of the class. So body for constructors has arbitrary expressions and members of the class. After the constructors phase, body only contains members, as in fields and methods. Does that answer your question?
Yep, thank you.
Okay, one more thing which we didn't include yet is the self-type. So in Scala, you can have a way to refer to this, which is not by saying this, you can actually give a name to this, like this. And you can actually specify that your this has type different from what you would assume it would have. So, you know. So what it says here is that, well, type def was a big example because I only to write a lot of type. So what it says is that foo inside itself somehow knows that when the foo will be created, it will additionally be an ordering of it. This feature is used a lot when you want to build something which is quite complex and is built out of the parts which themselves have a value. I can give you one very good example from Dotty itself. So Dotty has a notion of context, which I'll talk about later, but what more or less it does, it encapsulates the state of compiler at the current moment. State of the compiler in the current moment can be broken apart into several substates, which are the state of the phases, the state of the symbols, which is what happens with denotations. And you can actually describe those separately for most of the things. But because there are actually some interaction between those, you need to know that in the end it will all be mixed up in a bigger thing, which is this context. This is called a cake pattern, and there are several cakes inside Dotty. The biggest one is context. The other one is inside pattern metric. Okay, now going back to the trees. So the self represents the self type. It's worth noting that similarly to how we talk about semantics, self-type will be there in the untyped tree, and it will be for some type there in the typed tree. Later, it will disappear. The reliable way to get the self-type is through types. Everything that has to do with semantics, everything that has to do with what does a thing mean and how it behaves, should happen through types. And the way it's called is self-info, but we'll go into those details more when we'll be discussing the types. Okay, and the pre-body, which contains the actual body of the template. Similarly, we can decide to read it lazily, in order to save on doing work which is not needed. Now, there are some trees which we didn't go into, which will be rarely seen by people who work with the pipeline, but they will still describe what they do. The import is a tree which says that you import a namespace. To the best of my knowledge, only a typer needs to be concerned of those because it defines what kind of symbols are visible. And one of the very early phases in Dotty pipeline gets rid of imports. Package def is a tree which defines a package, which can have classes inside. I'm not aware of any transformation which would do to packages except of flattening inside lambda lift, inside flatten. So, yeah. Annotated. In case you have a tree which has some annotation, then you have, well, the tree which represents what you annotated, and the tree which represents how did you annotate it. Now, the tree which doesn't happen in syntax, thicket. That's a helper tree which allows you to return multiple trees in a location which you would expect to return a single one. It's very common inside Dotty that when you have a transformer, so let's see, transform. I'll go into those in more details later, but I'll just show you a thing. So this method is supposed to transform another method. Sometimes when you transform another method, you may decide to create multiple methods. And you somehow want to be able to return multiple methods, though you're returning a single tree. The way you do this in Dotty is you return a thicket. Dotty has internal parts of the framework, mini phases, pre-transformers, which are responsible of flattening those thickets. If you return a tree in a location where there is a list of trees, and you return a thicket, it will be flattened. If you return the thicket in a location where no list of trees is being expected, so let's say if you had a situation where you replaced a constructor with multiple methods, the compiler will throw. You're in a location where returning thicket is incorrect. Okay, empty valdef, a synthetic thing which you create where you have some kind of valdef which isn't given a value by user. And there are two helper trees here for it because those trees are used quite frequently and they can be shared and used as singletons. Okay, we're done with typed trees. We went quickly through the untyped trees. Now the question is, why do we need anything aside from trees? So,
sorry, I have a quick question.
Yes.
Okay. So all of the case classes, and I guess the basic tree class, they have this type member that is called this tree, I think.
Yes.
What is it used for?
Okay, so in Dotty we have multiple transformers which transform a tree by keeping the type of the tree. So let's say if you were to change the position of a tree, so there is a method called with pause. This is the text for hack. And because of it, it needs to cast it. Okay, so in short, this tree is used when you want to write a method which knows that it's not going to change the type of the tree. It's going to return the same kind of the tree which you started with. So for example, here, you're post-processing a tree in some sense. which means you'll return the same tree with slight modifications. You want to say that you're returning the same tree that you got before. Or here, good example, with type. The with type returns the same tree with assigned type to it. So it means that it returns the same tree, but the important part here that this tree addition allows you to say is that this tree is polymorphic. It allows, why we use polymorphism in trees is it allows us to know whether the tree is already typed or not. In particular, we have two values, untyped and typed. And you can say that you're returning a tree of the same kind, which is typed, though the previous tree used to be untyped. That's a common use case, and that's specifically what happens here. So with type returns a tree of the same kind, which is known to be typed. In our API, in many cases, we try to track, using the type system statically, whether the tree is typed or not. We have some APIs which are agnostic of whether the tree is typed or not, but in order to integrate with those APIs, with the APIs which require the tree to be typed, you want to be able to carry on the fact that the tree was typed and stays typed. And that's why this complexity exists.
Thanks.
Okay. So, any other questions?
Actually, I have another question. So, is there like a superclass that encapsulates the notion of something that is an L value, something that can be assigned to?
Okay, so we have different kinds of superclasses which don't really correspond to what the L and R values in C are. Let me show you them to you fast. So if we go to our example of ident, which I'll illustrate it to you, ident is a ref tree. Ref tree means that it's a reference to something. If you were to assign to something, you're assigning to something that you can refer to in the first place. So in case you were to assign to something, I would expect this tree to be either ident or select. So the thing which will be closer to your L value here, I would say, will be ref tree. But it doesn't necessarily, it's not necessarily one-to-one matching. The other kinds of trees which exist are the def tree, which is a definition. As you can see, those are the val defs, def defs are here. Other trees which somehow define the symbol are also here, like bind, it actually defines the symbol. And some of untyped trees, like module def, are here.
I just want to point out, if you want to actually know what you're assigning to, you shouldn't look at the trees. You should look at the denotation, or I mean the type which has the denotation.
Yes.
Right? So the tree is not a reliable way, even if it's a ref tree, it's not a reliable way to figure out what it is referring to.
Yes, that's right. So if you want to figure out what you're referring to, the most reliable way to do this is type. And that's the way which the compiler will use. Tree will more or less tell you how did you get there. But there are multiple ways to get there, and depending what you are, let's say A can mean different thing in different contexts. Because you have multiple variables named A in your project. And in order to know which A you're talking about, you can look at the type. It will tell you. So now when we started explaining something about the type, and we said something about R values and L values, it's an important thing to know that Dotty and Scala compiler type system is not in any way similar to C or Java type system. It's a lot more expressive. The type can tell which specific member do you refer to. In C, if you're saying that you're referring to something, the type that it has is the type of return value. So if you're referring to B and B is typed int, the type of B is int. In Scala and Dotty, the type of B is B. If you want to know, you can widen it to int, but you're not required to. So the types are a lot more expressive. We'll talk more about this in the future discussions. We'll be talking about the types. But important thing to you to know, don't build strong similarities between C compilers, let's say, if you know them. Okay.
Dimitri, so
yes, Mariana.
Another, yeah, since you were talking about assignments, so if I understood correctly, previously you said that in an assignment tree, the left-hand side can be any arbitrary expression. Did I understand correctly?
Yes.
So how is that? How can you have an arbitrary expression in the left-hand side of an assignment?
Let me write you an example. Okay, so I wrote quite a funny tree. This is your assign. You're assigning the field S, and your selector of what you're assigning to. This is a select, which has from what you're selecting is this entire expression. This entire expression contains class definition, it contains an infinite cycle, and then it creates whatever you actually did. So what I meant when I said that you have arbitrary expression, I meant that in subtrees of this tree, you can see all the trees possible.
Right.
At the same time, the top level tree actually explains what you're assigning to, but you can select it from anything, including this case.
So related to that, does the left-hand side have to at least be a ref tree? So here the left-hand side is a select with other stuff underneath it, right? But does it at least have to be a ref tree?
I intended to say yes.
For assignment?
Yes.
Yeah, if it's a simple assignment, yeah.
So important thing to know that when we're talking about assignments here, we need to be aware that there are assignments which happen before the sugaring.
Yeah, I mean, after the sugaring, it's a setter call normally, right?
Well, that's when you acceleration already.
Yeah, yeah.
So this is an also, so let's say if you have two, you can define and assign variables in Scala multiple at once. This is desugared by typer, but in untyped tree it still exists. So what happened here is I defined two variables at once, and I assigned two variables at once. This is still an assigned node, which on the left-hand side doesn't have a ref tree. You won't see these kinds of trees after typer, but before typer, they exist. So in most cases, when you're doing some transformation, you can assume that the left-hand side of the ref tree, of the assign is the ref tree, but if you're very early in the pipeline, in particular if you're between typer and parser, it may not be the case. Thanks for a good question. Any other questions?
Well, okay, I have a question related to that. So is that something that is enforced in any of the post conditions of any of the phases?
To the best of my knowledge, no.
Okay.
It would be nice to add it to first transform, and it would be a nice way to get somebody started to add this post condition. So we have this first transform, which is the first phase inside the compilation pipeline, which somehow prettifies the tree and creates new assumptions. One of these assumptions is the mode class and its companion always go together, and the class always precedes its companion object. That's the assumption that this thing creates, which wasn't required by user code before. It gets rid of imports. It removes named arguments. If it was to enforce such requirement, it would have been nice. Yeah, and if somebody was to start contributing to Dotty, I think the best way to start contributing is to add more post conditions, because by doing this, you check your assumptions about how compiler behaves. Either it's quite frequently that your assumptions will be wrong, and compiler will show you that you're wrong because your assumption doesn't hold, or you may be fixing actual bugs. So that's the best way to contribute, to start contributing. Any other questions?
Do you have a list of post conditions that you want added to the compiler?
Not currently, not at the moment. Generally, the idea is that you start by thinking what you assume to be a truth inside compiler. We want to allow you to start thinking and come up with things which you believe you can rely on. Then you go and try out this and see if it holds. In most places, if you're coming from other compilers, your first assumptions won't hold. Okay. Any other questions? Okay, let's proceed. So we have all those trees which are quite expressive and can express everything that user wrote. Why do we need anything else? The answer is when you're compiling, not everything is source defined. When you compile code written by user may use standard library. He may use Java standard library. He may use stuff which is in a separate file, which you're not currently compiling, though it's on your compile path. So you want to be able to somehow represent things which people can refer to, but you're not compiling them now. And in order to refer to them, we use something called symbols. So that's a symbol. That's a reference to a definition. This definition can be either a field, or a variable, or a class. In case that's a class, we actually have a class symbol, which has more information attached to it, which corresponds to the class. We also have the no symbol, which represents absence of something, and we actually have error symbol. Talking about errors, because Scala compiler and Dotty compiler are used when developing code, one of the things which is hard to get right when you're starting with compilation is you shouldn't assume that the program that you're compiling is correct. And while you're giving an incorrect problem, you should try to continue to compile it. For example, if you were to report errors, users want to see all errors at once. They don't want to just see first error and when they fix it, see the next error, because otherwise they will think that it never ends. You want to compile as much as you can, type check as much as you can, transform as much as you can. Because of this, in case you have a situation where you can't figure out what to do, and you want the compilation pipeline to continue, if you were to return a tree and you can't do a thing, you're going to report an error through the error reporting system, and you're going to return an error tree. Error tree will mean that you, instead of returning a thing which doesn't make sense, you explicitly said that you return a thing which is an error. The same happens with symbols. We have error symbols, we have error trees, we have error types. Okay, now, next discussing symbols. Important difference between Scala C and Dotty is that symbols, though they are reference to definitions and they uniquely identify a definition, they don't say what does this definition mean. In order to say what does symbol or definition mean, we have denotations. I won't go into those details now because we first need to discuss what are phases and types to explain this. But in short, every symbol is given a denotation, and this denotation explains what the symbol means. Every symbol at the current moment has a single sim denotation. This sim denotation may change over time if the symbol changes meaning. An example where the symbol changes meaning may be if previously you read the symbol from the class path, and you try to understand what does a symbol mean by reading the already compiled artifact. But now you're suddenly recompiling the same thing, and it comes from a different origin. It has different signature, maybe because you either changed it, and it has different meaning. Symbols can not only refer to terms, as in members, they can also refer to types. You can have member types, you can have classes. And in order to do those, well, you have methods which tell you whether you have a term or a type. One important thing to know about the terminology used here, when I say a class, I don't necessarily mean that the thing is a class in a source. What I mean is it's either a trait or a class or an object. The entire compiler, when it talks about class symbol or stuff like isClass, it means whether this will refer to a runtime object, more or less. It may be a trait, which will be compiled to an interface. It may as well be a class. In order to know whether that's a class or a trait, you ask its symbol, you ask its type, you ask its denotation. So I'll quickly tell you where this information is being stored for those who want to dive deeper on their own now, but this will be covered in future.
So a class symbol is always a type symbol, or what happens if it's an object?
A class symbol is always what, sorry?
Is a class symbol always a type symbol?
Yes. Yes.
Or can it be a term symbol?
No. So an object will be compiled into two definitions. One, which represents a class, which is underlying class of this object, and the other, which represents a term, which is a singleton of this value.
Maybe you could show the output of Xprint front.
I don't want to go into this now because it will ask multiple questions. I'll illustrate this. So let's say if you were to define an object O. After type checking, what will happen here, you'll have class O $, which will have whatever this O used to have inside. And you'll have a val, which is O, which is new O $. One trick which happens here is that this class has to know that it's O. So it's actually something closer to this, which is important to type checking. So everything inside this class knows that it's going to be this val. So this will be a type, and it will have a type symbol. This will be a term, and it will be a term symbol. And those two, you can go between those two through the API. It will allow you to navigate between them.
Sorry, how can you have this order type if you don't have an O? I didn't understand that.
You have the val O.
So this O is a reference to a val. This is a singleton type, which represents this val.
Yeah.
And that's one more example of types in Dotty and Scala being more expressive than in C. Okay, now what I was saying is I don't go into details how this information is stored, but I'll quickly show it for those who are willing to find it fast. So symbols refer to denotations. Symbols contain denotations. Denotations refer to what symbol it have, refer to where the symbol is defined, so who's the owner. Let's say if you have a member of a class, it's owned by the class. If you have a field inside the method, it's owned by a method. A variable inside the method, it's owned by a method. And you have flags. These flags actually represent some semantic things which are commonly used and commonly accessed. They are an optimization in the sense that they could have been represented using other ways, but because they're so frequently used, it's very inefficient to use an object for them. So in order to know where something is a trait, you will actually ask whether it has a flag trait, and you will check a single bit here. To know if a field is mutable, you will check whether there is a flag set mutable. There are a lot of flags like this. The flags are finite, so we're very careful about what do we put inside the flags. Some flags are reused. We know whether a symbol defines a type or a term, and if something applies only to terms, and something applies only to types, we can use the same bit to represent different things for terms and types. So to give you a nice example which doesn't need interaction. So some methods may be bridge methods, which are the ones which you use to implement the interface of your superclass, which may be less precise than zero. If you have a method which implements this forwarder, it will have a flag bridge set. Because types never implement parents, they never implement more abstract members of parent, you don't need this flag every certain type, and you can use the same bit on types to represent whether you have successfully and fully defined a type of a type. Okay, so that's an example. Denotations also have the type. So when you're talking about what's the meaning of a term or a tree, what happens here is you're actually either asking the type of the tree, or you're asking the denotation of a tree, or you're asking flags of the denotation of a tree, or you're asking the type of a denotation of a tree, which should be in most cases the same as the type of a tree. It may not be the same in some cases where you for some reason decided to lose precision. I won't go into details here, but sometimes this happens.
The type of the denotation and the type of the tree? Is that what you said?
So you have the tree, which has a type. The type itself has a denotation. And the denotation inside the type of the denotation may be slightly different. We'll go into these details later.
Okay, thanks.
Okay, now we have 1 hour of our time, so we covered most of the stuff that I wanted quite in time. Let me cover the next small topic, which is kind of unrelated of what's going to be covered next month, so I think it's perfectly fine to cover it now. Okay, so when you're compiling your source, you're going to mutate. You're going to have several stages of compilation. Those stages are represented by phases. The source, which is written by user, is first parsed, and you get some tree which represents everything that the user wrote. Then it's type checked, and you get a new tree which represents everything that user wrote and what does it mean. And then the pipeline starts. This pipeline is represented by all these phases which go after. Some of these phases execute on their own. There is a single thing which executes, and it executes. It entirely contains what happens after it finishes. Some of them execute in blocks. We have many phases, which we'll talk about later. But the point to know is those things actually are somehow joined, and they transform the tree together in order to have less transformations be formed and less trees recreated. They exist on a single traversal of a tree, and they have a single result created as whole composition of all these transformations. That's how we modularize the compiler. In order to make compiler easier to analyze, we split it in small things. Let's say we have here a phase which has actually like 30 lines of code which creates the getters, which is used with another phase, which replaces sequence literals, which is itself 30 lines of code. Those two are two different transformations. Each of those is simple and self-contained. So you want them to implement them separately and reason about them separately. At the same time, you don't want them to execute separately because they do a very small thing, and if you were to traverse and transform the entire tree for the small transformation multiple times, you would be slow. That's why we block them. Okay. Now, when we block them, and we have this tree which goes through all these phases, we want to somehow represent that the same thing had different meanings at different time. In order to know, to say different meanings of time, we need to have a notion of time. A notion of time in Dotty is period. Period represents a phase which you are currently describing, but it can as well represent a block of phases from and to. So you have the last phase ID and phases before last, which tell where does a phase start and where does the phase end. Additionally, you have a run ID. Run ID tells you something about Dotty compiler. Unlike many compilers, Dotty doesn't assume that after you compiled your thing, you throw everything away. Dotty assumes that you may use the data that you learned from previous compilation when you compile something new in order to compile it faster, so that you don't need to recompute this data. Run IDs represent these different iterations of when you compile new stuff, you add more and more knowledge. You may ask, why do we have 7 bits to represent phases and we have 17 bits to represent runs, while you won't have thousands and millions of compilations a day when you compile a project? Well, actually, this is intended to run inside IDE, and every time you make a key press, you have a new run which type checks stuff. So this 2 to the power of 17 runs is actually the number of key presses that you have until you need to throw away the compiler and create the new one. Okay. Yep. There is also magical phases such as nowhere, which represent that something doesn't mean anything nowhere. We also have magical ways to say that something is valid forever. But as far as I remember, that's a flag. So, okay. So that's a short intro of what Dotty is. Now, after we've discussed what Dotty is, I'll give you several illustrations how to use it. So, as I was saying, you clone the Dotty, then you clone the Dotty library inside the subfolder Scala, and now you're able to compile it. You compile it using the call compile, which will, yes?
Is there a brief document that summarizes these steps that could be updated in the future when the steps change?
A document that summarizes what?
Well, what you have to do to check it out and check out this Scala library.
Yeah. So if you go on the website,
started document.
There's a docs link at the top right, and there's a getting started page, and also a workflow page, which sort of describe all of this. And currently, it's not super well presented, but we're going to try to update the documentation very soon. Yes, to make this nicer. And also, if you have questions, you can always come to the Gitter channel. So it's gitter.com.
I mean, it's just if someone watches this video a year from now and the procedure structure has changed.
You should go to the website and everything should be clear because we have updated everything and everything is good, hopefully, in the future.
Yes, so we're currently thinking how to integrate IntelliJ itself into our CI to ensure that somebody can set up IntelliJ reliably. We've recently had a situation where setting up and importing a project in IntelliJ got broken, and for those who imported before, everything worked fine, but we didn't see it. So we want to make sure that we're, with every change we're testing, that it can still be integrated in the CI. Trying to figure out if it can be done. Okay, so you compile it with SBT after you reverted everything that I modified and stopped compiling. In particular, apparently I deleted a single line. Dotty has multiple subprojects, a lot of them. You can run tests for every of those separately, or you can just say test. It will run all of them. It will run tests for Dotty itself, it will run tests for documentation tool, it will run everything. It takes quite some time to run. On the machine that I have in front of me, it takes 10 minutes. I'm not going to make you wait for it to finish. The way how I develop it personally, and the case which works best for me for fast iteration time, is that there is a useful test which doesn't include everything, but includes most of the stuff that you'll be interested in. If you ask SBT to package everything, it will know about which tests you have, so auto-completion will work. That's why I'm asking you to package. So there is a test called a file code called tests, which contains common tests, which is actually the entry point how most of our testing works. If I'm interested to work in a specific test, what I commonly do is I isolate it here, either by commenting out others or by creating a new one, and I work on it. So the way how you invoke it is you say taste only .c tests, and you start running it. You see, some tests started running. Now, for me, it comes very handy if I was able somehow to attach a debugger to a running test. It gives me a huge bump in productivity. If I have an issue, I can somehow find the way to analyze it. So to give you an example, I will create some funny assumption somewhere here in the unexpected location. And I want to make it possible to analyze what happened here. So I'm going to add triple question mark here, which will throw. Now I'm going to kill the test and rerun it again. In order to know where it dies, I'm going to show you what I promised. I said that I'm modifying a build a lot. And that's how I do it. So you open your build. How do I get the thing back? You open your build, and here you have one of the only things which survived through 2 years in our build. This line. If you uncomment it and you reload your project, which will recompile the build file, now every time you run something, it will pass these arguments to the JVM, to the start source. And what this argument does, it says, before you start running, wait for a connection for 5005, and only then continue running. So suspend until you have somebody connected. What it gives us is that if we were to try running tests, you see it recompiles Dotty, and then it tries running it packages it, and it tries running the test. It says listening for transport socket, blah blah. Now what you can do is you can say, you can add new debug configuration in IntelliJ. You click remote here, and by default it actually uses port 5005. You can give it a nice name. And now, when you see debug, it actually continues, it connects to the VM that runs your tests and continues running. As you see, our stuff fails because we added exceptions. Now, what we can do is we can create breakpoints. One way to do it would be to, add a breakpoint somewhere and wait until it hits it. Yeah, I placed a place where it rarely happens. So I'm putting a breakpoint to a place which is commonly used. Yeah, you see? Yeah, so.
How much more time do we? We're gonna have to switch to a different room.
I'm planning to finish in 10 minutes or so. I can try to speed it up and finish in 5.
Well, or we could take a break and of 5 minutes, but okay. Well, keep going.
Okay, so now you see the breakpoint fired. So you have the entire debugger here. You can.
Is it? Again.
Yeah.
Oh, wait.
Just click it on here, right next
Yeah.
to it.
Well, now the okay.
Okay, so you have the entire debugger here. You can expect the state of variables. The important part, which is nice, is you can evaluate arbitrary expressions. Okay, so what was supposed to happen is it would show me, showing me the window. And here, you can do whatever you want with everything that you have around. You have TP1, and you can call all methods on it. I don't know, TP1.symbol. It doesn't have a class symbol, but it has class symbol v. So that's a very handy way, if you have a bug, to understand what happens around. Another handy way is you can not only make breakpoints on specific locations, you can have exception breakpoints, which happen if you throw specific exception. So in particular, our triple question mark throws not implemented error. So if I was to continue, it actually normally runs faster, but because I'm yeah, see, it was able to find a place where I throw this exception, and that's a place where I added my triple question mark. It comes very in handy if you have some kind of strange exception coming in from nowhere, because you can stop it there, and you can ask it questions. Once again, you can evaluate arbitrary expressions and see what were assumptions of you which were wrong. Okay, I propose to finish here. If you have any questions, please ask them now. But otherwise, we can take them over to the next call.
Well, thank you very much.
Thanks. Yeah, that was very useful.
Anyone with questions?
So you can also always ask questions on the GitHub channel, which is linked from the readme on GitHub. So like join chat link.
Yeah. Okay.
Great. Thank you very much.
Sounds good. Thanks.
Bye.
Bye-bye.